Hi, I'm Santos. I work at EMC Insurance, and I'm going to be talking about how we use the Wolfram language to explore different Insurtech technologies. Hi, my name's Santos. I'm going to talk about how we use the Wolfram language to explore different Insurtechs. So again, I'm Santos. I do insurance here. This is the EMC Insurance building in Des Moines. EMC is a property and casualty insurance company. They have branch offices mostly centered throughout the Midwest, but really covering pretty much all 50 states. It's just a little bit of background on me. So I originally started off as a physicist. Spent the first however many years of my career in academia, jumping around from different small liberal arts colleges, finally getting a tenure track position in Iowa and at Simpson College. Had an opportunity to collaborate with some folks from EMC Insurance, and they said, hey, why don't you come aboard full time? And you know, if you had asked me when I was in high school, I was thinking, I got a chance to go to an insurance company, and I thought, this is the most boring people I've ever been around. I don't want to do insurance. I'm never going to do insurance. Insurance has changed quite a bit. It is the thing I like to tell people is I learned more in my first 6 weeks working at an insurance company than I did in my previous 6 years in academia. And the reason is that insurance is very different than it used to be. This is not your grandfather's insurance company. These are some of the technologies that we've gotten to explore just in my couple of years there. So if you look at the top left, that's Lisa Simonetta. She's our Senior Vice President of Claims. She just sponsored a workshop looking at virtual reality headsets for use for the claims department. On the top right, we were also looking at augmented reality. We think there's going to be a lot of opportunities. So things like you have some sort of damage to a building. With augmented reality, if you can set it up correctly, you can overlay the original property versus what it looks like now and get a sense of what the change was so that you know and can process that claim faster. Insurers are also doing a lot of work with drones. So a lot of times a hurricane comes through some states, you can't get in necessarily to see the damage that's been done. It's very easy to take a drone flyover or an aerial flyover, look at that aerial footage. So we've just started a drone program at EMC that allows us to look at roofs and other things that are difficult to get access from if you're just having a person walking on the ground. We're doing a lot of work with satellite imagery. Obviously, if you're insuring a property, the amount of risk you take and the amount of payout you're going to have to do to replace that building if it gets damaged depends on the material, the construction type, the square footage. These are things we're starting to be able to detect now over just using satellite footage and things like Google Street View. I'm going to go through some of the things that I've been playing around with using the Wolfram language. And I'm going to start with just some analysis of satellite imagery. So as I mentioned, building evaluations are based on their square footage. Typically what happens is we will send a person out, and that person will go, they're loss control folks, usually of an engineering background. They'll go out, they'll physically measure the building, then they'll go and reconstruct that in CAD to do an evaluation of how much that building is going to cost to replace. And the thing we were interested in is, can we do this a lot faster and make it more scalable? So right now we do about 10,000 properties each year. We really want to get that up to the 100,000, and we're not going to have the personnel to do that. But what you can do fairly quickly, and this is something that Wolfram actually helped us, we hired them to help us build the code. Right now we can just pull in a satellite image. I'm going to cheat a little bit here. So the original plan was we were going to use satellite images and construct a neural net to detect the outline of those buildings. I'm going to cheat for this talk just because what we found is that the neural nets are great if you have tons and tons of training data. We didn't have that, but it turns out there's some cheat codes, which is basically the Google roadmap view, which gives you the outline of the building. And that gives you a way to build training data very quickly. So I'm going to use the roadmap from Google, and we just create a bunch of different functions. So you've got construct a mask from that roadmap. We're going to detect the center building in that mask. We're going to find the closest point to that building, visualize the area, compute the area, and then we also have some functions that can deploy this as an API. So I'm just going to run these quick. And if you want to see what that mask looks like, this will just take a second to run. And you can see we get not only the building, in this case a school, but we get some of the field houses that are next to it. Anything that shows up in the mask, you can start to detect the area of. So I'm just going to have it detect the center building. I'm going to ignore those other two smaller buildings there because it's the center building we're really concerned with here. We can start to highlight that on the mask and compute what the area is. So we're doing this just by pulling images, usually satellite images from Google, off and doing some analytics on them. A lot of times what happens is if you've ever used the Google Maps satellite view, it's not great at necessarily picking out the exact building you want. So what we've done is made a session where you can be a little bit more interactive. So let's say you pull the building out. One of the things I like about the Wolfram language is it gives you a quick way to make these interactive apps. So you can just select the building you want. You can take a look at the outline. If I decide I don't want this building, I want to move it down and look at this building over here, I can do that. If I want to look at the area of both images of both buildings, I can do that as well. So that's some work that we were doing with satellite imagery. But we've been doing a lot of work with image processing in general. And one of the big problems that we've had is just being able to label data very, very efficiently. So machine vision requires a large amount of labeled images. And if you're trying to do classification, that's not so hard to deal with. But if you want to actually segment the image and figure out something like an area or how big something is, you need to do mask making, which is very time consuming. We were having interns do it, and we were basically torturing our interns. They were taking hours a day and only getting through 100 images or so. We've found a way to reduce that, the time it takes to make a mask to under a minute in some cases, just by using manipulate and the locator tool, along with image foresting components to select different regions of the image. So here's an image that one of our drones pulled. It's images of a roof that has some ponding issues. So I'm just going to run this really quick. Now what I can do, just very efficiently, I can select, I'll say I want to look at ponding. That's a ponding spot, but this is not ponding. And you can see we can start to build masks very efficiently here. So this upper region over here, that's not ponding, that's not ponding. This over here in the extreme end is not ponding. So you can very quickly label images. This is something that if we had an intern doing it, they would be sitting there trying to make polygons around the ponding region. And it just takes forever. This code makes that so that you can get through 30 images an hour, and it makes it very, very efficient. So that's a lot of work that we've been doing internally. We also do work partnering with outside groups like startups. One of the companies that we really love is a Des Moines-based company that does some really innovative stuff in the wearable space. They're called MakeYouSafe. Their basic idea is they have a little armband that you can put on. It's small, so it's not too intrusive. If you're working at a manufacturing plant, it has a little sensor that you can plop in there, and it measures just different things that could be associated with potential losses for the company or potential accidents. So anytime there's an incident, the device triggers that. And incidents could be something like extreme temperatures, could be humidity, so that you might get some mold if the site is too humid. It could be a manual report, so it's the employee senses something's wrong, maybe they trip over something, they can push a button and report an accident. Motion, which is the one I'm going to be talking about, so detecting slip, trips, and falls, which are some of our biggest hazards. Noise that's too loud, light detection. So if it's too dark, that poses a slipping hazard, and that can lead to lots of losses as well. So the different motion classifications they have could be people are running, people are walking, slipping and tripping are the ones we obviously care most about, and then also no movement. So the way the device works is it detects the different incidents, it identifies and provides some feedback that allows the manufacturer or wherever the site is to take prescriptive steps to improve the safety at the site. So on our end, that's going to reduce the number of claims. So we don't build the devices, but we did spend a little bit of time working with them, helping them, and giving them feedback on the machine learning algorithms they were using to detect slip, trips, and falls. So I'm going to talk about that for a little bit. So the wearable device that they have has a really nice accelerometer that can measure your XYZ position. So you might get a graph that looks like this. If an incident is triggered, a lot of times it just happens that the device happens to get bumped, so you get a big spike in the acceleration, which will cause that incident to be triggered. But sometimes it's just the person walking. If it is a slip, you get a different characteristic signature. And we're using that time series of data and some classification procedure, some machine learning technique to classify, is the person just walking or did they actually slip? So MakeUSafe had their own proprietary algorithm that they put together. We wanted to compare against that. So you can do, we did a quick just visual of what sort of data they were getting. And then we tried to figure out what was actually happening in their data, doing a little bit more of a deep dive. So if you look at the coordinate system on the wearable device, there's an x-axis that's pointed forward, y is pointed up, and then z is pointing into the body. And one of the first things we found in their very first run of data that they've since fixed is we were getting this screwy data. So the acceleration is measured in units of g, and you'd expect that, so g is the acceleration of gravity, which is pointing down. That's in the negative y direction, so you would expect to get -1 all the time if you're just standing there. Now it's never quite exactly 1 because people are holding their arms like this, and then the device is not quite pointed straight up and down, or as they're walking, they're moving their arms back and forth. So you would expect it to be close to -1, but not always exactly -1, usually a bit less than -1. And what we found when we were averaging some of the curves, in this case I think it was for the slip, was that sometimes we were getting things that were almost always +1 instead of -1. I was like, that's weird. So it turned out we could quickly identify just that some people were putting the device in upside down. Which, small thing, easy to correct, but that's the type of things you want to do. You want to learn early in a pilot. Talking to insurance folks, they don't necessarily have physics background, so it's difficult to visualize what that coordinate system looks like. But again, we can build some very nice, fast visuals where we can say, all right, this is what it's going to look like if the person's wearing it on their left arm. You can see the green axis is what we're measuring in the y direction. We should get that for gravity, but look, if that's upside down, that's going to flip the device. Also, you got to be careful whether you're wearing it on the left arm or the right arm, because if you put it on the right arm, all of a sudden your x-axis is backward. So simple things that are easy to correct and easy to classify and do on the fly. So it shouldn't matter whether you wear it on the left arm or right arm. You can automatically detect that just based on how the accelerometer data is appearing, and then just flip your axes accordingly. To check their machine learning algorithm, we had like a little bit of a mini internal contest with our data scientists. We try to have like sort of small Kaggle-ish competition. It's funny. We'll have I made this little paper crown that's like you get to be the king of the data scientists, king or queen of the data scientists, and they'll get really excited about this paper crown, which is like just poorly made. But we did an internal contest with this, and just to set a bar for it, I just used Wolfram's internal classify function. I think this is going to come out. Yeah, this is going to give me an issue. I don't know why this is doing this. Come back. Try this one more time. I used Wolfram's internal classify function, just threw it up, and we gave them a day to analyze the data. And what we found is that most of the data scientists we have are using tools like R, which take a bit more manipulation to get them to run really well. Wolfram's classify beat all of our data scientists. So I should point out a couple of things. These are not their actual names. I didn't get their permission, so I pulled a lot of funny names offline. But I think that's one of the real powers of Mathematica, though, is that with very little effort, you can get reasonably good results. Now, to give our data scientists a little bit of credit, they were busy with other stuff at this time too, so they might have put in just like an hour of work. If they put in more optimization, I'm sure they could have done a better job on this. But it shows the power that what you can do with Mathematica very, very quickly, since it's so very high level. Another area we've been focused on quite a bit is doing, back over here. Yeah. Oh, yeah, sorry. I meant to change this, and I apparently did not. So the 1 through 5 are the different classifications of movement. So I forget which is which, but I think 1's walking, 2 is slipping, tripping, falling. Oh, the input is the data that's up here. So you're taking the X, Y, Z accelerations, yeah. Correct. Exactly, yep. Yeah, good question. Sorry, I didn't make that clear earlier. So another area we've been looking at is doing natural language processing and text extraction from documents. So we have just terabytes and terabytes of unstructured claims documents. And we have nurses that will have to put together these medical timelines. And they measure their work literally in stacks of paper. So how many feet of paper did you get through in this week? Obviously, if there's anything we can do to help them out and automate that process, that's something we want to consider. And we've started working on this a bit. It's tricky because there's not a lot of structured data here. But one of the things that is structured is there are these healthcare finance administration forms. That's about 8% of the documents we get in for any sort of injury case. So they tend to be a bit more common, and they're very structured. So I have a fake one here. Again, having fun with one of the data scientists on my team. Are you not going to let me enlarge? Well, I'll just run it, and then you'll see the larger form. One of the data scientists on my team had fun with the names here, so there's no HIPAA compliance or other things we're going to have to worry about. But as you can see, it's a very structured form, and if we can just pull out the information from the different boxes, we should be able to pre-fill our databases with the information from those. One of the problems is that usually we get these as paper documents that get scanned in, so they don't even necessarily have OCR on them. A lot of times they're handwritten, so we have to find a way to manage all of that. First thing we do is just detect, is the document a HCFA form, which we can just do with the classify function. I'm going to run this now because this one takes, oh, did I forget to run? Let's get my form. I seem to be missing code in this. Oh, yes, thank you. I switched the order of it. So there's a lot of functions here. I'm not going to go through any of them because it's going to take way too long, and I think I'm already running out of time here. But if anybody has questions, we can talk about that later. But what we can do is, my data scientist, Parky, put a lot of work into standardizing this form. So a lot of times when they get scanned in at an angle. Using the image lines function, it's fairly easy to correct for that part of it. So this takes a little while to run, but we should see a more standardized version of this, and I think it takes like 10 seconds on our machine. There we go. So it binarizes the image, uses image lines to get it in the correct orientation. And from that, we can start detecting different fields. Now, if you look at this form, you can see a lot of times, if you look at, for example, the telephone field over here, there are extraneous lines that we have to filter out. And so we put a lot of effort into just imputing extracting out the lines that are there, the stray marks, and imputing those values. And also I'll walk you through what that kind of looks like here. So let's say we wanted to extract the address field. The first thing you do is you just do a crop around that field. So you might get something like this, which you can read fairly easily. We convert that to, we color negate that, and then the text recognizer is usually pretty good at pulling that information off. You can do a similar thing with the names. Again, I didn't pick the names here. But things like that stray mark will sometimes mess up your text recognize, so we try to get rid of those. Again, you color negate, and then it can pull. The text recognize usually does a pretty good job of pulling those names off. Here is kind of an extreme case where a lot of times you'll have the line going right through the text. So that text recognizes generally we found not going to be able to handle. So you have to do some work eliminating that line, and then we tend to use the inpaint function, which does a pretty good job of filling in the blanks once you've gotten rid of it. So this is a ICD-9, ICD-10 code, which tells you the type of diagnoses. And then the beautiful thing is that once we've gotten through extracting this information, all of a sudden we can connect to Wolfram Alpha, and you have that whole knowledge engine that you can go and say, all right, well, what is this diagnosis code? What are the demographics of the people who have this disorder? What are the height and weight? And then we can start correlating those other variables to things like what's going to be the time to return to work. Is there anything we can do to help improve that return to work time? So I'm gonna stop here and open up for questions, but I'll just end with a quick story. So just as a summary, this is not your grandfather's insurance. We're doing a lot more things in the innovation space with drones, and I spent the last 2 months looking at augmented and virtual reality, which never would have associated that with an insurance company. Wolfram language is a great tool. I wouldn't work with anything else for rapidly prototyping new tools in any sort of innovation space. And one of the things that I learned very recently is that the Wolfram language really spoils you. And we were having a meeting with an IT consultant, and he wanted us to show him how we deployed our API. And we did a cloud deploy, and it sent something up. And he was like, no, you got to show me how you deployed the API. And we were like, we just did. And he could not, he's a really smart guy, could not wrap his head around the fact that you could just deploy an API from within the system that you were coding in. So I think, at least for me, and you guys maybe have experienced something similar, there's a lot of techniques in the Wolfram language you just learn to take for granted. But then when you see people who are programming in Python and R and all they have to do just to get to the point where they can deploy models, it really gives you a sense for the power of the language. So I'm gonna go ahead and stop there, and I guess I will just open up for questions.